Hi, I'm Bill Kinney, and this is the 14th video in my series about helping people practice problem solving to study for Actuarial Exam 2. We are doing problems from this book, The Mathematics of Investment and Credit, 6th edition by Samuel Broverman. In this video, we're looking at problem 1.5.11, ultimately solving for an unknown effective annual interest rate, though I also want to have a broader perspective on things like I did with the last video. I want to add more to this. I want to look at some functional, graphical, and numerical relationships between our fundamental quantities. I'm going to assume these are effective annual quantities in this video. I is the effective annual interest rate, V is the effective annual discount factor, and D is the effective annual discount rate. I have talked about D in the past couple videos. If it's new to you, you should watch those videos. Unlike the last video where I did the general review first and then I solved the problem, here I'm going to solve the problem first and then do the general overview of these functional and graphical relationships. Bob borrows $1,000 from Ed at an effective annual interest rate of I. It doesn't matter whether this is compounded more than once per year. The effective annual interest rate I is all that matters. It's what's going on as far as I being the effective annual interest rate and 1 plus I being the effective annual growth factor. He's going to repay it in full at the end of 1 year, but he's broke at the end of 1 year, so they agree that he's going to repay it 1 year later, 2 years after the start, in such a way that the effective annual discount rate D in the second year is numerically equal to the interest rate I in the first year. So they have the same value even though they are different ideas. At the end of the second year, Bob pays $1,200. What is I in the first year? That is the goal. Oftentimes we make number lines to help us solve these problems, but you really don't need one in this problem. You've got the $1,000 at the start. We're going to find that, first of all, the future value of that 1 year in the future would just be 1,000 times 1 plus I, the effective annual growth factor. And then, as we talked about in the last couple of videos, now if the effective annual discount rate is D, to get the future value 1 more year in the future, you'd multiply by 1 minus D to the negative 1 power. Again, if that's new to you, you will want to watch videos 12 and 13. This kind of expression will represent the growth of the $1,000 for these 2 years, no matter what the ending amount is. But this is now equal to $1,200. And we have the fact that they were numerically equal, so I can replace D with I. I can divide both sides by 1,000, and I can say 1 plus I over 1 minus I equals 1.2, or 6/5 if you prefer. It's a pretty easy equation now to solve for I. We can just cross multiply. Not sure why this was a starred problem. It's not really too hard. I can write this as 5 plus 5I equals 6 minus 6I. I can then add 6I to both sides to get 11I on the left, subtract 5 from both sides to get 1 on the right, and I must then be 1/11th, which if you use your calculator is 0.09 repeating. All right, so that solves the problem pretty quickly. Now let's do our broader overview of ideas and relationships here, which is helpful for problem solving, so I think it's worth your time. Let's review our main quantities here. I, again, is the effective annual interest rate. 1 plus I, then, would be the effective annual growth factor. It's what you need to multiply any amount by to get the future value 1 year in the future. We have V, the effective annual discount factor. It's a function of I. Let me go ahead and give that function a name. Let me call it f of I. We have seen that it's 1 over 1 plus I. This is the thing you need to multiply any amount by to bring it back into the past, to discount it to the past, to find its present value now if it is an amount 1 year in the future. Effective annual discount, present value discount factor, you could call it. Put PV right there. Present value discount factor. New quantity, D, that I've talked about in the last couple of videos, is the effective annual discount rate instead of factor. We've seen it's I over 1 plus I. Let's call that function G of I. I over 1 plus I. This is the effective annual discount rate. All right, there are our main quantities and the functional relationships between v and I and then d and I. We also have solved this equation for I and this equation for I to find I as a function of v and I as a function of d. Those would be the inverse functions of f and g. Let me just write the answers that we got. I as a function of v is f inverse of v. It's worth knowing two formulas for this one. This one's 1 over v minus 1, which is probably the quickest formula to use if you've got v in your calculator already and you want to quickly find I. It also happens to equal, if you get a common denominator of v, 1 minus v over v. And with this one, I is a function of d. We have seen in the last video that that was d over 1 minus d. I'd like to now focus on d as a function of I and I as a function of d here for the rest of the video. I'd like to graph these functions. Of course, I could use the technology, and if you're good at graphing, if your calculus skills are good, or if your graphical manipulation skills are good in terms of thinking about where vertical asymptotes are and so forth, and horizontal asymptotes, you can probably graph these pretty quickly. But I want to do something else because it's something useful for the future. I want to think about the infinite geometric series that I'm writing down here, a plus ar squared plus ar cubed. I have talked about finite geometric series already, but here I'm going plus dot dot dot. This is an infinite sum. This infinite series can be shown to converge to a number if the absolute value of r is less than 1, and what it converges to is a over 1 minus r. So I'm assuming you know a little bit about infinite sums here. This is true if the absolute value of r is less than 1. What I'd like to do is I'd like to use this formula in both of these cases to find alternative formulas for d as a function of I and I as a function of d as infinite series, because it's going to give us insight into the way the graphs look when I and d are small. Let's take this one first. d equals g of I. How can I use this formula here? Well, compare this expression with this expression. They would be the same if you replace a by I and r by negative I. So go ahead and do that. Replace a by I and r by negative I, like this. And you will get that g of I does equal what I'm writing here if the absolute value of I is less than 1, which it always is in all real-life situations. And that simplifies to I minus I squared plus I cubed minus I to the 4th, etc. Now imagine trying to graph g of I without technology. You can use this. How? Well, think about what happens when I is close to 0. When I is close to 0, all these terms are small, but I itself is relatively big compared to the rest of these. For example, if I is 0.1, I was not 0.1 in the problem we solved, so this is sort of separate from the problem we solved, though we might get some insight about the problem we solved here. Ultimately, if I is 0.1, then I squared would be 0.01, I cubed would be 0.001, I to the 4th would be 0.0001, etc. They are orders of magnitude smaller than I, so when I is small, d is approximately equal to I. You can ignore the other terms. So the graph will go up with a slope of 1 and will also pass through the origin when I is small. Now, is it really straight? No, it's not. This is a nonlinear function, but it's approximately straight because of local linearity from calculus. It's got a slope of 1. If I gets a little bit bigger, then to get a decent approximation, you might have to include the second term, the quadratic term, ignore all the other terms. I minus I squared. The graph of such a function would be a parabola. The coefficient of I squared is negative, so it would be a parabola opening downward. You've got a bit of concave, it's concave down graph there when I is close to 0. And you could continue this process of approximation. Actually, the graph looks about like this. And in fact, if you think about the original formula, it's easy to see it has a horizontal asymptote at d equals 1 as I goes to infinity, though I is typically small in almost all of our applications, so you don't really need to worry about that part. What's probably more important for us, though, is the fact that, again, at I equals 0, this has got a slope of 1, so it's below, and it's concave down, so it's below the graph of d equals I, meaning that for any small positive I, and in fact even larger positive I, the corresponding d, the corresponding discount rate, is smaller than I. For example, if I is 0.1, d is going to be smaller than 0.1. We can go back to the original formula to figure it out. It would be, if I is 0.1, looking up here, it would be 0.1 divided by 1.1, it would be 1/11th. If I is 0.1, d is 0.0909. Now, don't get confused. 0.09 repeating was what I was in the problem. Okay? But if I is 0.1, d is a bit smaller, and it's 0.09 repeating. Again, d is going to be a little bit less than I. I should see sort of the opposite thing happening if I think about expanding this thing as an infinite series. I is g inverse of d. Look at this formula and compare it with this one. Those are going to be the same if you replace r with d and a with d. In other words, you're going to get d plus d squared plus d cubed plus d to the fourth plus d to the fifth, etc. if the absolute value of d is less than 1. So if you now graph I as a function of d, it's going to have a slope of 1 at 0 and be concave up. Though you already knew that, these graphs are going to be reflections of each other across the 45-degree line, though we are labeling the axes differently, so you got to be careful about thinking about that. And yeah, the line I equals d is below this. So once again, this is sort of the flip side of the previous observation. If d is some small positive number, then I is going to be a bit bigger. If d is 0.1, so that d squared is 0.01 and d cubed is 0.001, etc., you could use this to approximate I. It's going to be a bit bigger than d. For example, if d is 0.1, you'll get 0.1 plus 0.01 plus 0.001. It looks like if d is 0.1, I is 0.1 repeating based on this. Okay, you can do similar kinds of things with these functions up here. Although with this one, if you're going to use the geometric series formula, it would be tricky. And we aren't typically wanting to expand around v equals 0 anyway. You'd probably prefer expanding around v equals 1 because v is more typically going to be close to 1. But I thought it was worth doing for these two things to again see that I is typically bigger than d in our applications. In these situations, it definitely is bigger than d. Coming back to the original problem, is there a tiny bit of insight that we can glean from this? I guess what I wanted to focus on here in a minute or so is the fact that d and I were equal in this particular problem, they were numerically equal, means that the I for the second year is going to be a bit bigger than the I for the first year. Since I and d are numerically equal in this problem, these two numbers ended up being the same, but they are corresponding to different interest rates for different years, for the first year than the second year. Since I is a bit bigger than d for the second year's I, the growth in the second year is a little bit more. The growth in the first year is 9.09%, essentially. What would the growth in the second year be? Let's see here. So if the $1,000 grows by 9.09%, the 1,000 is grown to 1,090.9 after 1 year, and then grow to 1,200 after 2 years. How much does it grow by that second year? What's the percentage of that? Let's see. Let's put a negative sign in front of this thing. Let's add 1,200 to it. It grows by $109.10 as a percentage of the starting amount. it grows by about 10%, a little bit more than it was the first year, which was 9.09%. So a little bit of insight into the fact that in this problem, the growth the second year is bigger than the growth the first year.